Hello friends, our next topic is angle modulation. As we have already discussed about amplitude modulation, that is a type of linear process. But here the angle modulation is a non-linear process. In this process, the angle of the carrier wave is varied according to the message signal or information bearing signal. So this is a definition of angle modulation, that is a process in which the angle of the carrier wave is varied according to the message signal. Now we note a point. In angle modulation, the amplitude of the carrier wave is maintained constant. So this is an important point. While in case of amplitude modulation or AM, the amplitude of the carrier wave varies instantaneously according to the message signal. And this is a basic difference between amplitude modulation and angle modulation. In angle modulation, the amplitude of the carrier wave remains constant, but its angle varies according to the modulating or message signal. Now, one question is arising in our mind that why we need angle modulation as we already have amplitude modulation technique. So the answer is, angle modulation provides better performance or discrimination against noise and interference as compared to amplitude modulation. Also, in angle modulation, there is improved noise performance, and this is obtained practically by means of exchanging channel bandwidth, which is not possible in case of amplitude modulation. But in angle modulation, the improvement in noise performance is achieved by enhancing system complexity, which increases the cost of both transmitter and receiver. So this is a drawback of angle modulation, but it increases the noise performance at the cost of transmitter and receiver. Now we are going to discuss angle modulation mathematically. The angle modulated wave is expressed as S function of t equals to AC cos theta I function of t. This is called modulated sinusoidal carrier at time t. Here AC is called carrier amplitude and theta I function of t is called instantaneous angle at any time t, and it is a function of message signal. So this is an angle modulated wave. In this there is a angle, and this can be represented in phasor form. Here the carrier amplitude AC rotates and completes its oscillation whenever angle theta changes by 2 pi radian. So we can say that the angle modulated wave is a rotating phasor with some angular velocity, and this angular velocity is denoted as d theta I upon dt with respect to time, and its unit is radian per second. Now we are going to discuss average frequency and instantaneous frequency, and can be obtained by using instantaneous angle. For this, we consider a small time interval delta t. At time t, we consider angle theta I function of t, and at time t plus delta t, we consider angle theta I function of t plus delta t. And the difference is delta t, that is small time interval. And accordingly, we can find average frequency in hertz over this small time interval from t to t plus delta t. Hence, the average frequency is denoted as f suffix delta t function of t equals to theta I t plus delta t minus theta I t upon 2 pi delta t. So this is a formula to find average frequency in case of angle modulation. As we know that the angle modulated wave is in the form of S function of t equals to a cos theta. In place of theta we can write omega t, and in place of omega we can write 2 pi f. So we can write theta equals to 2 pi ft, and here the frequency is equals to theta upon 2 pi t. And with the help of this, we can determine the average frequency between 2 points having small time interval delta t. Next, with the help of this average frequency, we can determine the instantaneous frequency denoted by f suffix I function of t. For this, we simply take a limit delta t tends to 0 with average frequency, which means the instantaneous frequency is obtained at some instantaneous time, and it is equals to 1 upon 2 pi limit delta t tends to 0 within bracket theta I t plus delta t minus theta I t upon delta t. Here we take 1 upon 2 pi outside the bracket, and the bracket with the limit is called derivative of instantaneous angle with respect to time, and this is equals to d theta I upon dt, and this d theta I upon dt is nothing but angular velocity of rotating phasor, and its unit is radian per second. So we can say that the instantaneous frequency f suffix I function of t equals to 1 upon 2 pi d theta I upon dt. Next, we note a point. Here we consider unmodulated carrier, or we can say without modulation. For this, we take message signal equals to 0, and the angle of this unmodulated carrier is given as theta c function of t, which is shown in phasor form. Here the rotating phasor AC make some angle phi c at t equals to 0, that is initial time, and after some arbitrary time t, the phasor rotates by an angle 2 pi fct with constant angular velocity. So we can say that the angle of unmodulated carrier, that is theta c, is equals to 2 pi fct plus phi c, which is same as instantaneous angle theta I function of t, because here we consider unmodulation or without modulation. But in case of angle modulation, we require a message signal. So before modulation, the carrier is given as c function of t equals to AC cos theta c. In place of theta c, we can write 2 pi fct plus phi c. And after angle modulation, the angle of the carrier signal is changed according to the message signal and become angle modulated wave, that is denoted by st equals to AC cos theta I function of t. Here theta I function of t is called instantaneous angle that varies with respect to message signal or modulating signal. Next, we discuss classification of angle modulation. Angle modulation is basically divided into phase modulation, that is PM, and frequency modulation, that is FM. Now first we discuss phase modulation or PM. Phase modulation is the process in which the instantaneous angle, that is theta I, varied linearly with modulating signal, that is MT. Now, as we know, before modulation the carrier angle is theta c, and it is equals to 2 pi fct plus phi c. Here phi c is the angle of unmodulated carrier at time t equals to 0, that is initial time. And for our convenience, we set phi c equals to 0. So the carrier angle is equals to 2 pi fct, that is called unmodulated carrier. And after phase modulation, and according to the definition, the instantaneous angle, that is theta I function of t, is varied linearly with message signal. That is denoted by Kp into Mt, where Kp is proportionality constant called phase sensitivity factor of the modulator, and it is measured in radian per volt. Because we know that the instantaneous angle theta I is measured in radian and the message signal is measured in volts, so the unit of Kp is radian per volt. Here the first term is called the angle of unmodulated carrier. So the instantaneous angle in case of phase modulation is equals to 2 pi fct plus Kp into Mt. So after substituting instantaneous angle in angle modulated equation, that is S function of t equals to AC cos theta it, we get a phase modulated equation. The phase modulated equation is S function of t equals to AC cos within bracket 2 pi FCT plus Kp into MT. Here within the bracket is called a instantaneous angle in case of phase modulation. And Kp is called a phase sensitivity factor of the modulator measured in radian per volt. Next classification of angle modulation is frequency modulation or FM. Frequency modulation is the process in which the instantaneous frequency, that is Fi, is varied linearly with the message signal. So we can say that the instantaneous frequency, that is Fi function of t, is equals to Fc plus Kf into Mt. Here Kf is proportionality constant called frequency sensitivity factor of the modulator, and here it is measured in Hertz per volt. And the first term is the frequency of unmodulated carrier. So in case of frequency modulation, the instantaneous frequency is equals to frequency of unmodulated carrier plus Kf into Mt. Now, as we know that the instantaneous frequency is also related with instantaneous angle. That is given by Fi function of t equals to 1 upon 2 pi d theta I upon dt. And from here, in order to determine the instantaneous angle, that is theta I, we take integration on both sides and shift 2 pi to the left hand side. So after this arrangement, the instantaneous angle theta I function of t is equals to 2 pi integration Fi function of tau into d tau, and we take a limit from 0 to t. Here tau is another time. Now we put the instantaneous frequency, that is Fi function of t, in place of Fi function of tau, and we get theta it equals to 2 pi fct plus 2 pi kf integration m tau d tau. So in FM, the instantaneous angle has two terms. First term is the angle of unmodulated carrier, that is 2 pi fct, and the second term, that is 2 pi kf integration m tau d tau, depend upon the message signal and increase or decrease in instantaneous phase theta I function of t. So accordingly, the FM or frequency modulated wave is given as S function of t equals to AC cos within bracket 2 pi fct plus 2 pi kf integration m tau d tau. Here limit is from 0 to t. Here kf is called frequency sensitivity of the modulator and measured in Hertz per volt. Next, we see the comparison between amplitude modulation, phase modulation and frequency modulation waveform that is produced by a single tone. As we know that for a modulation process we require carrier signal and message signal. Carrier wave is a high frequency sinusoidal signal that is shown in figure A. And for our convenience, we take a sinusoidal message signal of very low frequency as compared to carrier signal and shown in figure B. Now, first in case of amplitude modulation, that is double sideband suppressed carrier, the waveform is in the form of an envelope. Before modulation, the amplitude of the carrier is constant. But after amplitude modulation, the amplitude of the carrier is changed instantaneously according to the message signal and called amplitude modulated wave, that is in the form of an envelope. Here we note a point. In case of amplitude modulation double sideband suppressed carrier, there is a phase reversal or 180-degree phase shift at every zero crossing of message signal. So in double sideband suppressed carrier, there is a phase reversal as shown in figure C. And amplitude modulation is a linear process. Next is phase modulation. Phase modulation is a nonlinear process. In this, the amplitude of the carrier remains constant, but the instantaneous angle varies linearly with message signal. As we have seen in figure D, there is a compression of the signal. This compression is at every point of complete oscillation in message signal. And in case of frequency modulation, the amplitude also remains constant, but the instantaneous frequency is varied linearly with message signal. So, for every positive half cycle of message signal, we have compression, and for every negative half cycle of message signal, we have expansion. So, there is a variation of frequency with respect to message signal that is shown in figure E. Here also the frequency modulated signal is nonlinear process.